Okay, let's start and let's try. First of all, okay, this should disappear. And we've seen part of this talk, we mostly follow it, but no, we're not going to get to classification and band predictors, unfortunately. And we've seen part of that. Oh no. Okay, no, okay. Let me improvise. So trustworthy AI, right? Why it is interesting? Why I'm interested in conformal predictions is partly because of trustworthy AI. Unfortunately, that interest falls in that topic that is hard to pronounce, although when I'm interested just without knowing the actual topic. So the more we use it, the more we want to rely on it with some confidence, I guess. So we trust is a difficult concept, even philosophically. Too many devices. But if we hire someone to do the job, we want to trust them, whatever that means. And so with AI, we want some kind of transitive of that as well. We want to trust the AI. And how do we make AI solutions trustworthy? What does it mean to be trustworthy? And explainable AI and this FAT XAI, those two fields kind of trying to dig and get to the core of the problem of what is fair, accountable, transparency. Okay, that's the definition. Well, interpretability. Okay, recognize key properties of trustworthy predictive models. Interpretable models make it possible to understand individual predictions without invoking explanations. Framework models. Okay, understand is a difficult word as well. I guess here we want humans to understand individual predictions, not the models to understand and humans. Yeah. Well, if a model is interpretable, inspection analysis becomes straightforward, or at least that's how we define interpretable model. If it's both ways, if inspection and analysis of the model is straightforward, that means the model is interpretable. So we want to get to reach to that point. And yeah, we're building external explanation frameworks, saliency maps, etc. Right? I know, no, you're here for a reason, right? So you can throw things at me. Mm-hmm. So now, FAT principles. There's a whole website in the footer there. Include accuracy as a vital component of accountable algorithms. That's understandable, sort of, right? But the intuition, there is a paper.
I just
yesterday. There is a paper that came up just yesterday. That's why I'm. But I didn't have time to read it. So I want to, because what we do is like, well, the algorithm has to be very accurate, or at least reasonably accurate for us to even talk to it. You have to like get to a certain level before we're interested, right? So the accuracy is a component, and there the paper.
Yeah, I guess, well, they were more talking about like classification accuracy. Like, I think accurate in this sense doesn't just have to be classification accuracy.
No, but I think even in that narrow sense, accuracy or classification accuracy or regression accuracy, still the model has to be accurate. It's just not everything. But it's
yeah, that was actually, I think, largely also the point of that paper.
And then one guiding question for accountable algorithms is how confident are the decision output by your system. And the confidence here is a very difficult word, because like when you teach machine learning, students of machine learning tend to take at face value the score as probability, or score of the model as confidence. And actually, those usually those scores are not calibrated, that have nothing to do with probability, they have nothing to do with confidence, they're just a number, and we'll see that. So that's why at least when I teach machine learning, I stress that point. It's just a score, it's just something that model science, you still need to work with it. So trust, not just everything with the accuracy on top, but also ability to, at the very least, report uncertainty. This is very hard though. even for humans, right? Sometimes we discussed that last time. Sometimes we're sure when we're wrong, but at least uncertainty is a good thing to report. And if you go back to pack learning model, then there are two parameters there, epsilon and delta. But basically, you can't be epsilon accurate if you got wrong training sample. Like you've done as best as you could, and you have some uncertainty measurements based on your training data, but you got totally non-representative data and you failed. So there is still a possibility for that. And also, we want individual recommendations. So we want not just on average some accuracy expected, but we want, if we're predicting cancer or lack of cancer for this patient, we want to be able to reason about that specific prediction, not that the model is accurate on average. So the requirements for those models is if we want models to be fair, accountable, and trustworthy, they have to be interpretable. Well, decision trees, rule sets. People say that linear regression is interpretable as well, but mostly those who spend a lot of time learning about the linear regression and how it works. But if you go to a person who sees linear regression first time ever, it's very hard. You have to go through a lot of explanation because of multidimensional spaces, etc., etc. And the models have to be well calibrated, and that means that their predictions have to correspond to probability somewhat. The probability of error, I will show that. And the models have to be specific. That is, their predictions have to be, or their uncertainty has to be addressing or talking about individual predictions. And they, of course, have to be different depending on what this particular input is. And then also the models shouldn't be changing their opinions on the same inputs. The models shouldn't be like continuously adapting and changing their weights, because if we inspect the model today and then look at the model tomorrow with the same question, but the model has changed by then it will be impossible for us. That's kind of a questionable, understandable for us. We want to sort of cripple the model, freeze them, but then we're preventing continuous learning in a sense. This point prevents continual learning. But then I understand why. Like audit will become very difficult if your model is always a different model. It's continuously learning. So calibration of models of modern neural networks. That's from a different part, but we do that. There is we're still trying to get to conformal predictions, but we need those parts. Like, why the conformal predictions, and what is currently done? The one part out of all of those requirements that we're addressing here is that we want the model to return confidence in prediction that corresponds to probability. I'll talk about it now. And we want the model to return uncertainty. Conformal predictions will give us both of the things. So confidence calibration, the problem of predicting probability estimates is a representative of the true correctness likelihood. We'll define it mathematically. So why do it? We want just what I said, probability associated with the predicted class label should reflect ground truth correctness. And we need it for model interpretability. So if we had a perfect calibration, what would it be? Imagine, like I gave you a perfectly calibrated model in supervised multi-class classification. Input is some sample X from all of your data points, X. I could do my usual, this is a set of your samples, this is a set of your labels, and it's a multi-class classification problem. There is an unknown to us generative distribution that generates, it's a joint distribution, labels and samples come from it, generated from it. And this is an easier way for us to think about it. If we pick up a thing, we'll look at it and then we assign a label rather than, okay, label. You can condition any way you want it because you don't know, there might be some interdependencies, but that's more natural way to think about it. So an neural network is some predictor, some hypothesis that takes X and returns a pair. Now it's kind of a different pair. This is a guess that the neural network makes a guess about the label of that sample that it looked at, and then this is the score. Or if we want to interpret it, it's the guess of the neural network of probability that it's correct, or probability, probability that this X has that label. So basically what we want in the perfect calibration is that given the neural network output score of P, the probability of having the label be equal to the true label is P. So it's just what I said, that's we want the neural network to actually output the probability, like for all of the probabilities that it outputs. Old topic, people thought about it since we have all the detection, etc. Reliability diagrams. It's a visual representation. I'll show you reliability diagrams. 83, and the paper that I'm using for this couple of slides is 2005. The diagrams plot expected sample accuracy as a function of confidence. So if the model is perfectly calibrated, probability of predicted label to be correct, given the score is that score or that probability. Yeah, it has to be a diagonal. sklearn has calibration plots by default and as a function, and we have those calibration plots for models trained on the same data. And I assume even to acceptable similar accuracy, but they're different scores. Diagonal is perfect. It's whatever I predict is the actual observed frequency of the samples. And like when you see, sometimes the model is overconfident, sometimes the model is underconfident. It assigns like a random forest, interestingly, is kind of a sigmoid. When it gets to high confidence, it is more confident than it should be for probability. So it kind of making more mistakes than it should. And when it has low confidence, it's making less mistakes in terms of the prediction, in terms of probability, etc. So in this 2005 paper by Nicolescu and other guys, they looked at the old models and the new models, and they figured out or found out that the new models are highly miscalibrated. So neural networks give us high accuracy. They're correct, but they judge their score doesn't correspond at all, or hardly ever corresponds to the probability of the correctness of that prediction. So you have to, if you want to interpret that score, you have to recalibrate, even though you're using softmax on top, etc., etc. It's not a probability at all. It's kind of, I guess, underconfident or overconfident on the higher part. If you look at this confidence distribution, yes, it tends to assign very, very high scores. ResNet 2016.
With the softmax, kind of makes sense. You're kind of pushing towards that.
But softmax is supposed to model, if you look at logistic regression, it's supposed to model probability.
No, I know, but softmax, you kind of push it towards like always trying to predict one, right?
It's by model.
Right.
Yeah, like we're talking about here only one class, say, but so we're taking the probability of that class. It can push towards another class.
No, but binary cross entropy loss, for example, is also super bimodal. Either you want it to fully predict 0 or you want it to fully predict 1. That's when it gets the lowest loss. I mean, it kind of makes sense, I think.
But it is not bimodal here.
Well, it is extremely confident in.
Yeah, it's extremely confident in the class that it predicts.
Right.
Yeah.
But that's what I'm saying, you're kind of pushing it towards that, right? If you keep training it, like it'll at some point try to predict 1 every time it's a 1 class instead of 0.5. Because the binary cross-entropy loss gets smaller when you get to 1.
Labels are 0 and 1.
Right, exactly, yeah. If you make the label 0 and 1, that's what it's
If
gonna
the
predict.
labels are 0 and 1, it's trying to like
Yeah.
match that.
Yeah, it is trying to match that, but it still gets the samples that it's incorrect on, so basically it's just unable to differentiate those. Like there's a huge interval.
But this is why there's such big holes in like the manifold of like a lot of classifiers, right? Is that it's just like, it just needs to predict this one sample correctly. At some point, you're pushing it so far that it's not, it just creates this like dimensionality space that just has these little islands of like samples that it correctly classifies. That's what people are in out of distribution learning and stuff are looking at, is that there's like lots of holes in.
But this is overfitting, right? It's practically overfitting. It's just
Yeah, but is it though, like if it's also
it's-
correct on the validation set, most people would say it's overfitting, so it's like this issue with OD, with out of distribution. I mean, that's kind of like overfitting, but I guess like you would test against overfitting using a validation set.
If you are limiting or pushing your prediction sort of correctness interval just to points, like to delta functions, that's overfitting. How can you even get the validation set, because it's a different point and it hasn't seen it, so it suppresses it. Right?
Yeah, but I'm saying like it's very hard to test overfitting. Because currently we oftentimes these models do that, like it's not a delta function, but it's like a little bit around the point. And then once you get outside of that hole, like outside of that little like support, all bets are off. That's also some issues with interpretability methods sometimes. Like if you take the gradient and you get outside of this support of the manifold, it's just doing something and we don't really know what. There was also a really interesting paper on this, which is called "Your Classifier is Secretly an Energy-Based Model" in 2014, which also looked at this and trying to correct it.
So, okay, now the conformal prediction, it's a slightly different way, I guess, to address this problem of calibration and miscalibration. So what it does, why it's interesting, it transforms classifiers and regressors into confidence predictors. And the good thing here is that classifiers and regressors is a very general term. Any classifier, any regressor, this is a meta algorithm in a sense. And then transform predictions into prediction regions. And so here's I will talk about it on a different slide again. But it does slightly different things, or it provides us slightly different things for regression versus classification. For regression, it actually gives us an interval for any regressor, confidence interval. Well, the interval, and we will talk about it. You as a user set up which confidence you want to have, and it gives you a confidence interval and a number. It tells you with this probability, your true answer is inside of that confidence interval. So you have another parameter that you're trying to set to get to the probability that you want, but that's with this definition, it's kind of clear why they call it coverage. Basically, they want to increase the probability that the true answer is inside of the interval that the conformal predictor or conformal regressor returns. So the truth is covered by that interval. So that when they say coverage, it's an overloaded term, but I usually think something else, but that's what they mean by it. But when they say coverage for classification, or well, people who work in the conformal prediction, what they mean is you have a set of classes, and it's easier now to talk about large set of classes, multi-class model rather than binary. For binary, they have Venn predictors because it's a problem, and I'll show you examples as well. What returns a set. Instead of returning you a label, it gives you a set of labels. If it's very sure, it gives you just one class. If it is unsure, it gives you two classes. If it's like very unsure, it gives you 3 or 4 classes or whatever number of classes, and says, well, okay, otherwise, I want my confidence to be 50%. And the model gives me one class and tells me with probability 0.5, this is your class. I'm like, oh, no, I want with probability 0.9. Oh, then 10 classes, it's one of them with probability 0.9. So it's kind of counterintuitive, but like the more certain you want to be, the larger the area, because it wants to cover the truth. The goal is to give you the set or subset that does contain the truth with that probability. So that took me some time to wrap my head around what they're talking about. And okay, every prediction associates a measure of confidence with it. So gamma confidence prediction region contains the true value with probability gamma.
Question. Okay, so at face value, it seems like returning the set of, oh, these are the ones. You might as well just return the probability value, but it's more about it returns the joint distribution that is most likely to contain your actual answer, right?
No, it returns a set of labels.
Is it the conditional? Yeah, but in doing that, they might as well just report the actual probabilities. But maybe, well,
You give the y given x. And the
no. It's about the joint distribution over red, green, and blue. The joint
That's
distribution.
a conditional though on x. It's a joint. It's a conditional on x, but it's a joint between red, green, and blue.
Yeah. If it was just these are the 3 classes with the highest probability and they're over your threshold, they might as well just report the probabilities. But are they instead returning the joint distribution that gets over your threshold? So like if the joint distribution of red, green, and blue has some probability higher than your threshold, that's what it returns. Is that the point? Because otherwise it doesn't.
It's the promise and the guarantee, it gives you a set of labels that is subset of your original number of classes. And guarantees that with probability gamma, your solution, your true label is within that set. It's not doing like, oh, let's take one label and do binary one versus all, retrain everything. It doesn't do that. It's you're already trained your classifier yourself. You gave me your classifier. I forgot, I'll talk about it later, but it's not like, you're trying to reinvent the procedure. You're like, oh, let's assign the probability to each class separately, right? How do you do that? Oh, my model gives me a probability. No, it doesn't give you probabilities. Your model gives you some random score that has nothing to do with probabilities. We don't even need that score, and you'll see it in a regression example. We need a non-conformity score. We'll get there. Let's talk about, again, with regression. Imagine that we're doing, yes. So to me, counterintuitive part was, if I am certain in something, I'm automatically conditioned through years of study to visualize this. This means I'm certain, and this means I'm not certain in this value, right? So it was counterintuitive to me, like that for regression. Oh, if you want to be certain that you are here, your confidence interval will be this. If you want to be 99% sure that this is the value, or that in this value, will increase your interval and tell you, yes, your value, your true value is in this interval with high certainty. And if I don't care, it can give me this. Imagine tumor segmentation. So tumor segmentation, I have this, and there is a true tumor somewhere. Imagine this is true again. Think about this as true. And then if I don't care, if if I want to get my tumor with probability 80%, then it'll give me, okay, above this, with probability 80%, your tumor is there. If I want to be sure, and with 99% probability, it probably will give me something large. Like cut this out, and what I guarantee that you will get it out, but you're getting healthy tissue as well. That's a result. For the classification, which I'm not going to get into it because I found it not as intuitive, but more technical. Regression will give you a very good idea what they're doing and what the principles are. We can talk about classification next. But this is an example from a tutorial that I posted already. There are many tutorials, many things. So if an example is easy, then it returns just one label from the set of ImageNet classes. If the example becomes harder, as we see, it returns a set of labels. It also returns, this is not a gamma. It just says there is a gamma with probability this, the true label, which we don't know which one of them is true. With this probability, it's in this set. And when it's very difficult, the set of labels returned, and ImageNet is a good example of that, because with this 1,000 labels,
what exactly are the values signifying here? Like you, in the third case where we have the most difficult one, so it's like 0.3 and 0.22, which is Fox period. So in that case, what?
That's probably calibrated score of the model, but I don't think it's the probability. It's probably the score of the model that your neural network that gave you that score.
So even right now, with this information,
I'm
not able to interpret, or even the model is not able to interpret like what exactly the class is, right?
Yeah, it's uncertain.
Yeah.
As we want. If it's uncertain, we want it to be uncertain, to tell us that it's uncertain, and so that's what it does. I would ignore. I took it from the tutorial, the figure, and I didn't specifically read. I don't know if William read the details, because I was using YouTube videos and I was reading a book, but I would get confused and etc. So
How do you train these? Do you have to do any special training to make it give you confidence? Because I thought like softmax is sort of like known to have the tendency to be overconfident or something.
no, you don't care how you train it. If you train me, give me a bad model, I don't care what it returns, as long as it returns a number, a score, and I'll show it now. It doesn't matter. We will find out if the model is bad or
I
not.
think it's an add-on to models. I think that's.
It's a meta algorithm.
It's post hoc, right?
Yeah, it's a meta algorithm. Yeah. Nothing is retrained. Right. It's a decision procedure in a sort.
Because I was going to say, otherwise you kind of can also overfit on your confidence that your model, like if you train this to give you a confidence, then it can also just overfit on the confidence itself. Like,
I will give you anything.
right, exactly.
So this is the trick that I was confused about, and because all of the language in all of this tutorial is, to me, is wrong. It's misleading. They all talk about drawing samples, sampling, and things like that. And to me, it's a continuous process. I drew a set of samples, I trained, I drew another sample from this. No, like go back to those of you who took my lectures on computational learning theory, PAT, and when we set up the learnability models, we assume there is a fixed training and testing data set. So, and in the M there is a sequence. So observation space is a set of sequences. So you've got your training data sets, it's a sequence. You've got your testing, or you go into the wild and you still assume that there is no generative process that is active. You have the sequence. And then what I will tell you will make more sense. I couldn't make sense otherwise of it. Probability distribution, unknown probability distribution of those training sequences or sequences of data. And sequence of data is, again, we can write it as this, x1, y1, blah, 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 xm, ym, all right? the order doesn't technically matter, but it's more convenient to think of it as a tuple, as a sequence of pairs. And a scoring function. Notice there's no other condition on the scoring function, just a real value function, whatever. Right. So when we have that, here's what happens. Select subset from the training sequence. Actually, what I would do is from the test, because back to the out of distribution problem, the model I could have downloaded the model from Hugging Face, but my data is my data. I sample it from possibly the same, maybe different distribution. So I take my data. There is already a model given to me, or I've trained it before on some other data. I take my data and I select a subset from this model. 4 elements for now, just for the sake of example. I apply my scoring function. Notice that my scoring function is not the output of my model. It's just a separate thing. I will show you an example. And I get a real value for the score output. Then I sort them, rank order. And they all are on this, well, this is negative infinity, positive infinity. They fall somewhere. Now, the trick is that this is a fixed set. And thanks to Robin, I don't know if she's online, she helped me to kind of get my thinking straight. So because it is a fixed set, I don't have to know what probability this data came from. I just toss it in a bag and draw from the bag my next sample after I measured those 4 samples. What's the probability of my sample falling in between those other samples? So the probability is uniform. It can, because I'm drawing them uniformly, basically. They come from some distribution, but when I start taking samples from my testing distribution, they're uniform. With uniform probability, they can fall here, here, here. Like every interval now is equally likely for that.
They're
Then,
sampling from the same distribution that you were already sampling, like the.
no, I'm sampling from uniform distribution now.
No, I know, but I'm saying like, this
FC.
partly because, yeah, the under, yeah.
Oh, it doesn't matter. They could be even from a different distribution, but because I have a fixed set, I am taking them out from uniform distribution.
Yeah, I think we're saying the same.
If you take this out, sort it out, and then like randomly pick samples, well, anyway, so that was the key. I was like spending too much time thinking about it because sampling just doesn't work, and it's not a part of this conversation. And then we can express probability of my score on a given sample. Notice this is Z sample. It has both label and the value, the features. X, Z is a tuple, X, Y. I can express basically this probability, and this probability will be 2.6, right? Because of this uniform property. So let's consider conformal regression. Let's use this scoring function. Absolute value of y minus h. H is your regressor, whatever. This is on X. So I'm taking Z, I, which is what? Feature vector, and my label. And I'm applying my regression function to my feature vector, and I'm computing absolute value of the difference. I could have trained my regression function using least squares, MSE, well, it doesn't matter, but it's just an example of a scoring function, real value scoring function. H is a regression model trained on some data. And I have this, then I can express, as we said, what is, for a new sample, I have my calibration set of 4 samples, as before. For a new sample, pardon my typesetting, it's X. For a new X sub I, I know what my score, what's the probability of my score being like less than alpha 3 or less than alpha 4. I can compute it from there. That's okay. But those alphas have real values, right? My score on my calibration set return those values to me. Then what I can do is I can take my regressor also gives me a value, and my alpha is a value, and I have the probability. But from this, I can construct the membership. In order for this inequality to hold, yi has to lie in this interval. So suddenly, I got this confidence interval. I have a probability that I can assign to my regression function, which I didn't train, somebody gave it to be within that interval. And all I did was I took my data set, took a subset of that data set, gave it to humans to give me exact labels of that data set, of subset. 4 elements here, easy, right? I need the Y's to have the calibration data set. Here, when I have a new point X, I don't have the Y. That's what I'm guessing, that's what I'm doing. So that's kind of the gist of it. So how we actually do it? Okay, my animation broke ignore procedure. It will appear in due time. So training set, calibration set, and calibration set. And again, I read lots of bits and pieces, and this is from I link the guy Henrik Larsson, or like something I really liked. I liked his approach, so I'm kind of copying from his style of presentation. But don't, like, this calibration set, in fact, doesn't have to come from the same distribution, because this procedure will show us that our function, our regressor, is wrong. If our test set is out of distribution, then our confidences will drop automatically, because it will give us bad predictions on even like the calibration set will make sure it's correct. So the trick here is that your calibration set and your test set, or actually use data, have to come from the same distribution. But the training, anyway, doesn't matter. That's the beauty. And so if your calibration set is also drawn independently of your training set, and it has Q elements, and you have this non-conformity function, your scoring function, then here's the procedure. You have to have these 3 things: train a regression model, use H to compute the scores, or use that trained model to compute the scores on the calibration set, and sort the conformity, non-conformity scores in descending order. Now in descending order, I don't know why they flip it. That doesn't matter to me. So given Q calibration scores and a prediction for the new test sample. So this is YK. I guess I should do this. This is a prediction. We don't know the answer. I think. Oh, why didn't I? Okay. Then what we do is, let me.
So the, for lack of a better term, the support samples that they sample, does that come from the conformity or the training set?
From the calibration set.
Calibration set comes from your
The
test.
calibration set, yeah.
Test. So basically,
Yeah, the test set.
it's better come from your test set. Yes. Because then there is a correspondence of what your model returned here. Your model is your predictor or your regressor in this context, and what you will be using the next, what it will be returning. You're kind of calibrating. So once you have this, you are doing the following. That's the last thing I say before we over. You choose a desired confidence interval, epsilon in 0, 1. And then based on that desired confidence interval, you find an element here with your scores that is, this is like, well, epsilon quantile calibration score. This is tricky for me to interpret what they mean. But basically, when you find this alpha that is closer to your desired level of score. So if you want 0.8 confidence, if you want to say 0.9 confidence, but all you can use is this alpha. There is nothing closer to 0.9. So you're actually getting only that probability, that guarantees 0.8. It sums to 0.8 here. But usually what you do, you have around 100 samples or like few hundred, no more. Like you don't need 1,000 calibration samples and your error drops dramatically. Yeah.
So then I assume it's also important which sample you pick, because if you get a wider spread of non-conformity scores, that probably also helps with your downstream like confidence.
It helps you to where you can fall,
Right.
yeah, for your
So if you do
design.
very hard samples, for example.
But
very
you
hard-
want the IID, you want the IID for the theory to kind of.
Right, no, yeah. I'm just thinking like probably it is important kind of what the spread is of your non-conformity scores, and that depends obviously on both your predictor and on the samples you give it to compute the non-conformity scores.
Just let me write what they have there. So then you're saying that probability of your true label belonging to, well, they call it gamma, equals 1 minus epsilon. And what is gamma? Gamma is an interval. This is regression. Gamma is an interval around the true, around. This is true label. This is your estimated label. And this is the alpha S is the sample. This is the alpha that is closest to your epsilon. So probability of the true label falling within that interval that you determine by the alpha, plus minus alpha. We saw how we done it, right? We used the absolute value. It's simple algebra, very simple, kind of intuitive what is happening. I don't have the proofs. The proofs are there. They pretty much follow from that only statement that the probabilities here are uniform, and then the proof follows from that. Another thing, one more thing. Why is it good? Before we started late, and I will add classification as well to that. I will put online the full slides eventually. When we work with computational learning theory or with statistical learning theory, the main requirement, the main goal is performance on trained data. We want to have some guarantees how performance of trained data generalizes or leads to performance in the wild and in other data. But the main assumption there is IID. Like with all of the theory built, with all the proofs, they only work when the data is IID. Here, the assumption about the data is relaxed. The data only has to be exchangeable. It can be correlated. It doesn't have the probability of a sequence of your training sequence and of your calibration sequence is independent of the permutation, basically, of the elements in that sequence. And I'll look at them. There were some examples where they show concrete examples of the difference when it matters. So basically, correlations, your data can be correlated. It doesn't have to be IID, so that's cool. Yes, they look.
But you need to watch out that your sample isn't too biased, right? If you have a very small range of alphas, then your confidence is going to be your confidence interval is going to be very close because that's the alphas you have.
But you will know about that. it's.
No, I know, but if then you have, so if you take very easy samples, you may get like very close alpha spread, but then maybe on hard samples, the interval should be larger, but because you took very simple ones, your alpha spread is now very small, right?
So your confidence interval will be always large, it will be unconfident. It will not be
No, if you
incorrect.
take easy samples to do the calibration, it will be very small, even though it should be larger, that's what I'm saying. So if you take a biased calibration set,
No, in reverse, because
It'd be
you.
probably outside of the.
Yeah, they will be
So it's
outside, they will
very-
be too far, so the bound will be larger.
yeah, yeah, sure. But
I-
it is
I-
better to, but because you're dependent on where the alphas are, right? Because you can't say anything about the distance in between the alphas.
Yes,
It-
you are dependent on where. the
Right, so I'm
alpha-
saying it is better to get a hard calibration set so that you have a wider spread of alpha, so you have a better idea of what your actual.
Doesn't have to be hard, but it has to
No,
be
sure, I
wider.
mean, I guess hard for better. sort of-
But think about the following, for some applications, or maybe for most applications, I only care if we take the probability interval from 0 to 1, I only care about this part. I will always want to be, for some applications, I will always want to be super confident. And then for some applications, the difference may be, okay, the difference between 0.95 versus 0.96 may matter, right? And then you want your alphas to be all here, because people choosing those numbers all the time. But for applications where you have to cut more tissue, maybe you can sacrifice some.
Your alphas are how bad your model
You select based on your desired
is.
accuracy.
What you're drawing out is not correct. Like 0, 1 is the probability, which is dependent on the uniform distribution in between the alphas, but the alphas are how incorrect your model.
No, this is a calibrated value of confidence.
Oh, okay,
This is your,
Yeah.
the probability that you set. I want
but then
my
the alphas
answer.
don't lie on the confidence interval, right? It's the probability.
No,
between the
alphas is
alphas.
just
Yeah,
a
I was gonna say,
score.
okay. Yeah, I was
Yeah.
like, I was gonna say, yeah, it's about the uniform distribution in between the alphas.
No, well, think about this. If I want 0.9, or if I want 0.95, or if I want 0.99, doesn't matter. In this case, I will always pick this alpha.
Right, so
I
that's what I'm saying.
just don't have resolution there, but
Right.
it will be still correct.
Right, but the
It's just
wide,
like
so that's what I'm
there will not be
saying,
a
widespread alphas is nicer in a way. Because if it is closer to values you actually encounter in the wild, you will have a better, because you don't really know, like anything, let's say it's 0.40. You have to pick 0.12, right? There's no other, because you don't have guarantees about anything outside of that bound. Like that's still,
But that's just sampling a low number of your calibration set, like.
yeah,
we-
but
we have a
if it is
calibration
a
set.
biased set, it can also lead to issues like this.
I
really matter.
disagree with the word uniformly sample. It doesn't have to be, it depends on the task.
Yeah, because it's transforming the calibration or the distribution of the calibration set is already uniform.
No,
So
no, I
regardless, if you do that, if you have a 0.4 alpha, you're gonna have too few
No, I
samples.
agree, I'm not saying sample them biased, I'm saying if the samples themselves are easy for that particular predictor, you're gonna get lower
But
ones.
that just means you need to get better.
Yeah, but that's my point.
You just need more.
More,
To
yeah.
increase the bound.
Yeah.
So instead of doing 4 values.
I didn't talk about it,
26.
but they have a very tight bound actually. What
Or
this is a very
That just gets
intuitive
you-
sort of presentation of what is happening, and we already hung up. So imagine I was like, I'm suffering over it.
Because it's,
So they have both. They have both
It's not about the colors.
greater than epsilon, and a number here is I don't have it open. Do I? No, but the number here is kind of.
Well, let's say, like, if you have a really good test set, that also, or a really good validation set, that gives you a better idea of how well your models.
That seems to be out of the scope.
I know.
This number is slightly different from that number, but only like let me just hand wave through because I don't have the expression in front of me. Basically, if you even have like 100, it depends on samples, the in calibration set, and quickly, like exponentially quickly or something, if you have 1,000 samples, this interval is tiny, tiny, tiny. It just squishes it very quickly with the calibration set. So it's enough to have 100 samples. That interval between those probabilities.
Yeah, but that is obviously under the assumption that it's a representative sample of your true data set. And that's my point, is that in a lot of cases, that's not true for like real world applications.
Why? You have a training set or testing set already. You collect
Yeah,
it.
yeah, but those, I'm saying if those are, yeah, but so I'm saying if those are bad, then your calibration score is also gonna be bad.
Well, we're realistic, right? We only work with the data that we have.
No, I know, but my point is, it doesn't really solve the fact that
And-
data itself can be biased.
That is a problem for small sample data, so neuroimaging data or ECOG data.
I mean-
But if you go to like national.
No, this is not the training data. Go to the
No,
natural.
I know.
Start collecting natural data. You will be doing prediction on the natural data.
No, sure, so that's what I'm saying,
But
that
you-
makes it better, but I mean,
Rebuild your calibration data set.
yeah, but my point, that's my point exactly. I think people are gonna be using this as like a gimmick, like if you do this in your validation set in ImageNet, it's just gonna get like it's not gonna be a good calibration of your model.
The ImageNet validation.
No, I don't care about
sets
psychology
those-
here, right? People can do whatever they want. It's just mathematically.
Yeah, but
it's-
this set itself is like a very clean data set itself. I'm just saying, for example, Dolly, like what it's trained with is highly biased data set. So, and that's what you see in what it's producing, right?
That's
If you
okay.
calibrate it with that, then it's gonna be calibrated just for this bias distribution, like it doesn't circumvent. the
No,
fact that
take
it's-
Dali, take your distribution, manually label less than 100 labels, and then you will see that Dali is bad on your data, if it is bad. It will give you high uncertainty intervals. Well, Dali is not a regressor, and we only talk about regressors. So that's the beauty of it. I haven't seen that before personally, that you train it on one data set, and then you can detect this out of distribution by the calibration set, and like
No,
the
no.
only condition is your test and your calibration come from the same distribution.
No,
As
I
long
agree
as
with that, but if it's all elephants with a white background. And that's also all it's.
That is your data.
Set. Yeah, okay, but so my point is that obviously not elephants don't always.
I mean, the problem of data bad is always the same.
No, I agree, but I'm just
I don't
saying that it's
understand the
important
concern.
still, like to,
Yeah.
obviously, like most of our data sets are highly biased.
I would say the small data sets, especially
Yeah,
the
sure.
larger data sets, like, I don't see why Dolly would be biased because it's so much. It basically must capture the actual population.
Well, I can send you a couple papers. There's like.
I mean, I agree, like Dali and even like large models, GPT.
Yeah, it's-
They're highly.
Well, we
biased.
have to stop at some point. We're 15, almost 15 minutes over, and I'm recording. So let me finish
But then I
here
don't agree with
with
like conformal thing. I don't think it will even make a difference.
just like we're recording, right? Like if this got you interested, that's all I wanted with that. I think it's an interesting development. I haven't seen part of it before. It's very simple. It comes from the 90s, and it's kind of intuitive when you spend on it a lot of time. It becomes intuitive. So I thought that's interesting.
No, it is very cool. I was just wondering about like how.
But just like one question, one last question.